This is the presentation for the article, Does the Dataset Meet Your Expectations? Explaining sample representation in image data. My name is Anthon, and I will be presenting this with Das. The main questions that we are concerned with in this research is how we can understand our dataset. How can we understand the sample representation and the deficiencies of our data? Take, for example, a dataset consisting of vehicle speed profiles. Questions concerning the representation of the data might relate to if there are enough profiles that showcase a slow deceleration or a fast acceleration. If this dataset is to be used to train a safety critical component in some adaptive crew system, we should ensure that the dataset covers a sufficient amount of scenarios to ensure the reliability of the system. When working with safety critical components in traditional software engineering, there are a multitude of different ways to increase the reliability and our understanding of the systems. Due to the opaque nature of deep learning, though, these traditional techniques do not work. To ensure the reliability of a deep learning system, we need to supply it with enough samples of the scenarios of interest. Otherwise, it can be difficult to conclude that the system will be reliable and predict according to our intentions. This is a question about sample representation. Are enough scenarios represented in the training data such that we can be confident that the model will learn what we intend it to learn? And any lack of adequate representation is a form of bias. More specifically, sample selection bias. If you consider a toy dataset of hand-drawn circles and squares, how could we assess the representation of the samples in this dataset? If you want a deep learning system trained on this data to generalize the scenarios that we're interested in, we better have a good understanding of the dataset. As we can see from the figures, this small subset of the whole dataset, we can see that our dataset mainly consists of bright centered circles or squares. But what if we want to deploy our model in scenarios where the size and position of the object might greatly vary? So small off-center shapes can appear. For scenarios where the lighting conditions might vary. To reason and argue if our model will generalize to these scenarios, a first step is to understand what samples are present in the data. Do we have enough objects that are off-center? Are there dim objects? One solution to these problems comes from the annotations associated with each data point. Assuming that we were interested in the class imbalance between circles and squares, this imbalance could quickly be reasoned about since we can just check how many data points are annotated as circles and how many are annotated as squares, i.e. we could check the distribution of circles and squares in our dataset. The reason we cannot immediately do the same for more complex properties such as size, position, and lighting is due to the fact that this information is not available in the dataset. We lack those associated annotations. But for this simple problem with circles and squares, we can easily design labeling methods to obtain these extra annotations. By obtaining the bounding box and closing the object, we can easily get access to these extra annotations related to the size and position of the observed object. We can thus obtain the distribution of these properties of interest. And having access to the distribution of annotation, we can assess the sample representation. And to ease the process of verifying if this representation is covering the scenarios of interest and to gauge the sample selection bias, the engineer can specify a distribution of expectation which says which scenarios are expected to be covered. Any mismatch between the distribution of expectation and the distribution of annotations of our dataset is then an indication of sample selection bias. While we can assess the mismatch visually as shown here to the right, where the red histogram indicates the distribution of annotations and the gray is the expected sample properties that we expect to see. We also introduce an overlap index to ease the interpretation and help facilitate the understanding of the mismatch. The index measures the mismatch in support between the two distributions and indicates if sample selection bias is present or not.
Thanks, Anton. So far, we have seen how it is possible to explain sample selection bias if detailed annotations are available. But what if we are confronted with a data set where detailed labeling is not possible? We now show that even in such cases, we can explain bias using parametric simulation. We saw earlier how an engineer can specify expectations in the form of a distribution of labels. If we sample labels from this distribution and plug it into a function that can simply draw shapes, we end up with a set of simulated shapes that captures the range of expectations specified by the engineer. We thus see how parametric simulation essentially inverts the labeling process. If detailed labels are available, we saw how we can explain sample selection bias as the mismatch between actual and expected distributions of labels. Now, if labels are not available, we can instead explain the same bias using the mismatch between two datasets, one real and one simulated. So how do we detect this imbalance? We do it by using the idea of predictive certainty. We first use the actual dataset to train a classifier. We then use the simulated dataset as a test set. As the trained classifier predicts simulated samples, we see how certain it is in making its predictions. If the classifier predicts a simulated sample with high certainty, it is likely that samples with similar characteristics are available in the actual data. On the other hand, if the classifier predicts a simulated sample with low certainty, chances are that the actual dataset does not contain samples with these characteristics. However, our quest is to not just identify individual outlier samples. Rather, it is to see if outlier samples share commonalities in their labels. To make this determination, we turn to techniques of feature attribution. Specifically, by using a technique called Shapley additive explanations, we see if certain label values tend to push down predictive certainty. When we examine the influence scores of a handful of simulated test samples, we start seeing a pattern. Large, bright, and centered shapes tend to push up predictive certainty, and conversely, small, off-center, and dim shapes pull down predictive certainty. When we convert the distribution of influence scores into a probability distribution, we can see that the resulting distribution is a remarkably close approximation of the actual label distribution. So what have we achieved? Even in the case when a dataset does not contain detailed labels, using a combination of parametric simulation and feature attribution, it is possible to predict its distribution of labels. And having predicted this, it becomes easy to examine its sample selection bias. While this technique may work well on a toy dataset of hand-drawn shapes, it is fair to ask whether this technique is extendable to real-world settings. If we aspire to apply it to a sophisticated dataset of real-world images, the extension may be possible, but the effort required would be considerably larger. But that is not our target. The work we currently present is a spin-off from our work with fixed-length time series, which can be naively approximated using parametric simulation. For details, please refer to the linked article. It is now time to summarize and conclude. Models trained using deep learning are beginning to be used in a variety of applications. Under such conditions, it becomes important to verify that the data used to train these models are not hazardously biased. If we specify important characteristics of data samples, we show that either using labeling or parametric simulation, it is possible to expose such bias in a human interpretable manner. This allows engineers to take corrective action, helping improve the dependability of the trained model. Thanks for listening. Bye.